In this slideshow, we're going to look at how parallel lines can split up similar shapes, making proportional segments. So the situation arises when we have a triangle that is divided by lines that run parallel to one of the sides and give rise to smaller similar triangle and one or more trapezoids. So if we have triangle ABC like this, and we split it with a line XY, where XY runs parallel to BC, you can see that we have a smaller triangle AXY and a trapezoid BXYC. We can use the rules of similarity that you already know to see that the two sides have to be divided in the same ratio by this line XY. So we know that triangle AXY must be similar to triangle ABC. We know that because angle A is common to both of those triangles. And we know that angle at X here must be the same as the angle at B here because they're corresponding angles, because XY and BC are parallel. So, given that they're similar triangles, if we say that the measure of side AX is X and side AY is Y, then there must be some multiplier that changes AX to AB, some scale factor. And for reasons that will become clear in a moment, I'm going to say that scale factor has value 1 plus k. So then the side length AB is 1 plus k times x, and side length AC is 1 plus k times y. And if I say that it's 1 plus k times x, if this whole thing is 1 plus k times x, if you distribute that x, you get x plus kx. So this is x, and this little bit here must be kx. Similarly, if this is y, then this little bit here must be k times y. So our conjecture is that if two or more lines pass through two sides of a triangle parallel to the third side, then the intersected sides are divided proportionally in the same proportion on both sides. We can then use that for a question like this. In this following shape, find the unknown lengths. We're given some of the lengths, but not all of them. Well, you know from doing previous examples like this that the first thing we're going to do is draw out the separated triangles so that we can compare them as similar shapes. We're going to use the proportionality conjecture, and for the parallel sides, we'll draw out the triangle separately, but for the two split up sides, we don't actually need to draw them out separately. We can say that we know the ratio of each of these segments on the left side will be the same as the equivalent ratio on the right side. So 120 as a ratio with 45, so the top segment divided by the bottom segment on the left must be the same as the top segment divided by the bottom segment on the right. Solve that equation. A will equal 30 times 120 over 45, which equals 80. We can do the same thing for B. Second segment divided by the bottom segment on the left must equal the middle segment divided by the bottom segment on the right. So B is 45 times 40 over 30, which gives us 60. So we've worked out A and B using the segment relationships on the sides. C and D, we can't use segments. We can't because they're not on the two sides that were divided up in parallel. These are parallel lines parallel to the base of the original triangle. So for this one, we'll write in that we know that this thing here is 60 and this is 40, 80, 120. We'll write in all our values that we now know from those calculations. Now we can split up the two triangles away from the third major one. That was 120 and 80 and D on the top. The 120 plus 60 made 180. 80 plus 40 made 120 on that side, and we had C as its base length. And this was our original triangle. It might be useful to combine these lengths now. So that altogether is 225. And on this side altogether we have 150. Now we will be using similar shapes to work out the lengths of C and D. So we can say that to go from the larger triangle to the middle-sized triangle, we're multiplying 120 over 150. So we do the same thing to the base. C must equal 180 times the scale factor, which is 144. And we can do the same here. From 225 to 120, we're multiplying by 120 over 225. Do the same thing to 180. D equals 180 times 120 over 225. That equals 96.